Okay, so we will claw our way back to algorithms soon, and the reason why I went so far into deep structure theorem is that, so the question is, we learned something. This told us that if a graph G, okay, so this told us using this Bramble trick. So if you are given a graph G and you want to show a lower bound on the tree width, what will you do? You will try to find a Bramble of large order, not size, which has a large hitting set. Okay, okay. So as I try to tell you, right, we couldn't show. Okay, so here are some good consequences or the, okay. So what did we learn? We learned that the tree width of n cross n grid is at least n minus 1, okay, and at most n actually, because we did compute by this trick, and actually you can show this is equality holds, okay. Grid is actually equal to n. But this is what we managed to show. We actually showed an upper bound of n and we showed a lower bound of n minus 1 using the Bramble theory. Okay, I did not give you a proof for this, but you can take it as a fact. Okay, so what would like to teach you next? Okay, so why did I go so far? So clearly, if n times n is a minor of G, that implies tree width of G is at least n, right? If I have a n cross n grid as a minor, implies the tree width of G is at least n, because then arises, if someone told me, suppose I told you n times n grid is not a minor of G, right, is not a minor of G. Does it imply that tree width of G is function of n, which means if a graph excludes a n times n grid as a minor, does it imply that tree width, does that imply the tree width is at most f of n, right? Okay, or maybe let us write down t cross t grid, that is better. F of t excludes t times t grid as a minor, then this implies f of t, right? It is a natural question, right? We realize that if I would have used t as a max size clique, I could not expect such a theorem, okay. So in famous graph minor series, Robertson and Seymour showed that if G excludes t times t grid as a minor, then tree width of G is some function of t, where f was some doubly exponential function, okay. F was doubly exponential function. Let us not write doubly exponential because I really do not know what it was actually, okay, but it was some towers of exponential function, okay, some towers of exponent, towers of 2. But later in early 2004 and 5, f of t was brought down to 2 to the power big O of t log t, I think, okay. What does it mean? If G excludes T time T grid as a minor, then tree width of G is at most 2 to the power big O of T log T, right. So, if you exclude 5 times 5 grid as a minor, then what is the tree width of this graph? Some constant. It is not more than some function of 5, which is amazing. Okay. And all we knew at that point of time, okay, all we knew at that point of time is that the function f of t is at least omega t log t, okay, actually t square, omega t square. This is all that we knew, that this function has to be at least t square. And the big open question in the world was, is f of t some Pauli function of t? Okay. In 2014, in a breakthrough paper, not graph theorist, but Chandra, I think Chakuri, I am not writing his name correctly, okay, and Julia Chuzay, I am still not writing her name correctly, showed that f of t is k power 99 Pauli log k. Sorry, not k, t in the power 9. Then series of improvement, it got down to t19. So, this was some stock Fox 2015, and it has come down to t power 9 in Soda 2019. Okay. So, what do we know now? If G excludes T times grid as a minor, then tree width of G is T to the power 9 some Pauli log T. This is what we know. This is our current knowledge. This is our current knowledge. Okay. Again, huh? No, I cannot explain to you. I mean, to show a lower bound of t square, I need to give a construction, which I cannot give you a construction at this point of time. This is all that I am saying.
You have to give me a construction for grid?
No, I have to give you a construction of what? That a graph G which excludes some t times t grid as a minor and whose tree width is at least t square, right? I have to show, and I cannot give you this at this point of time. This is all that I am saying. It is some sort of expander graphs, but I mean, I don't know how to prove this. Let's put it this way. Okay. All is well. Okay. So here is a So, imagine yourself.
Consider a cube of size n. It has grid of root n cos root n.
Okay.
So, it is root n, right? T equal to root n. And then cube is n.
It excludes, right? It cannot have root n plus 1 times root n plus 1 grid as a minor, right? Definitely, right? Because it has more than n size, but his tree width is n minus 1. Okay, good. Okay, happy? Okay. But how many of you know Erdos-Posa theorem for cycles? So what is Erdos-Posa for cycle? What does it says? For every k greater than or equal to 0, a graph contains a graph contains either k vertex disjoint cycles or it has what? Or it has order k log k FVS, feedback vertex set. Okay? You can also prove such kind of theorems starting from this. Try this out. I mean, I will come back to this if I have time at some point of time. I will try to prove this. Okay? So, Erdos-Posa and these things are well related. Why? Imagine yourself, why will it imply something? Look, if the graph has large tree width, then it will have k vertex disjoint cycle because I have a big grid as a minor. It means take all these guys, take all these are vertex disjoints, right? So I can get a cycles from here. So you cannot have big, so your tree width is small. If your tree width is small, you can do some sort of divide and conquer to kill all cycles by poly t log t vertices. Okay. Anyway, but we had, so this is poly. Okay. Now people ask what happens, look at the same theorem, this is called planar excluded grid theorem, excluded grid theorem. Okay. Let G be a planar graph, okay, not anything, let G be a planar graph, okay, and then I would like to ask, look, any graph if excludes t times t grid, then it is bounded by t power 9, but if I restrict myself to planar graphs, do I get better bound, right? You get my question? So what is this? Let G be a planar graph. If G excludes t times t grid as a minor, then tree width of G is less than or equal to, I think it should be some 5t plus 6 or something, I have no idea what it is, but let me give you the right number. Does anybody know what is the number? Some 5k. Nine by 2. Okay, I think it is 60. Okay, I think there are better bounds from, but the book says 60, so for now I am writing 60. Okay, can you use this and say let G be a planar graph on n vertices, then tree width of G it does not contains root n plus 1 times root n plus 1 grid, so its tree width is 6 times root n plus 1. This is also called Lipton-Tarjan separator theorem. Okay, anyway, so we have seen some excluded grid theorems and we will use them to design parameterized algorithms, okay, but not now. Okay, but remember, what did we say? Remember, I was defining a notion of planar F deletion problem in the beginning, which I said that it has a property that it is an alpha covering for some fraction alpha. What was this? So F contains one planar graph, okay. This is all the thing which we assume. F contains one planar graph. Now input is G k parameter is k, and the question is, can we delete at most k vertices such that G minus S does not contain any graph f in curly f as a minor, right? This is what we said, right? So, look at a graph. So, what is the tree width of G minus S? So, S is those set of vertices whose deletion, what will be the tree width? Can you say something? Look at the tree width of G minus S. It definitely does not contain some fixed planar graph as a minor. Okay, so let us see. So, this does not contain H as a minor, where H is planar. Okay. Now, any planar graph can be obtained as a minor of some slightly big grid. Okay, any planar graph H. Okay. Okay, so here is another lemma or theorem, whatever you want to know. All this requires proof. I mean, and people can prove all these things. So, any planar graph H can be realized as a minor of 14 times vertex set of H times 14 times vertex set of H a grid. Okay. So, if I take 14, so if the size of H is something, if I take 14 times that times 14 times that as a grid, then I can get this H as a minor. What does this implies then? This implies this graph G minus X excludes, if mod H equal to H, it excludes 14H times 14H as a grid, which implies what is the tree width of G minus S? This implies tree width of G minus S is at most H to the power 9, some big O of H to the power 9 or 10, because there is some polylog T, right. So, but H is a fixed graph, so it is constant. So, basically any planar F deletion, if I look outside the solution, it has a constant tree width. Okay. And that is what, so look at feedback vertex set, which is just one example of this problem, where F is just a triangle, which is a planar graph, right. Tree width has 1. So, you can define a genre of problems with this, and because it excludes, now you will understand why when we were doing this dichotomy, like what we can, for which F we could design kernels and everything, why did we go and inserted a planar F? That is because that allows us to assume that if I look outside the solution, it has a constant tree width, hence I can do lot of things there. Okay. So, this was all that I wanted to tell you about some properties of tree width. Remember excluded grid theorem, it will be useful. Okay. I have not given you proof for any of these things, but it is beyond that I can give you. I mean, I only know proof for this of 2 to the power big O of T log T. I have tried to read proof of T power 98 10 times and I still cannot keep it in my head. Okay. This proof I can give you sometimes if you want. Okay. All good. So, now we are going to move towards algorithmic aspects of tree width. Okay. So, we have done all structure and we will use all this structure. So, what did we learn? We learn what tree width are, what kind of separation properties are, what are the obstruction to tree width, if those obstructions are not there, what kind of upper bounds we can achieve on tree width, right. And there is a min-max relation on tree width given by Bramble. So, if I need to show a lower bound on tree width of any graph, I should come up with a Bramble of certain order. So, you have learnt all these little tricks about showing lower bounds, upper bounds on the Bramble. Okay. And finally, we learnt about 2 excluded grid theorem. One in planar graph, other in a general graph. General graph, it says if you exclude some t times t grid as a minor, then tree width is t to the power 9 poly log t, and if it is tree width of G in planar graph, then it is linear. So look, this is why this is also called linear excluded grid theorem. Okay, and this can be extended to large families of graphs. We will get to that when we get there.
For any planar graph, it can be think of minor
Subgrid.
subgrid, right?
Yes.
So for then the tree width of any planar graph is root n.
Order root n. Yes.
Order root n. So even if it excludes the like, if I go to the grid, what I'm trying to say, why is that 60 optimal?
Is 60?
Optimal, like can it be better than 60?
Maybe 5, 4, but nothing better than some constant. I mean, I don't think you can make it better than say 4 or 3. Okay. Okay. So I'm going to rub everything on the board except the definition. Okay. So what do I want to do now? My input will be G and number T. My parameter is T. Output, either tree width of G is strictly greater than T, this I can tell you, or returns a tree decomposition of width. We will see. It will be some order T, but we will see what it is. Okay? We will see what this is. I don't know at this point of time. Let's look at the existential algorithm, right? What did we said? We started with some W. So if you recall correctly, we had a graph G and a set W, which we used to give as input. And the first point was, if W was less than equal to some 2t plus 4, we returned one node tree, right? Tree with one node root, and f of r being v of g, right? And what was our goal here? Goal here was to return a tree decomposition of width 3t plus 4 such that root contains W. Am I right? This is what we did. This is exactly what our goal was. And then what we did, okay fine, if W is say 2t plus, no, if W is less than or equal to 2t plus 4, this we did. Otherwise, what we did, if W was less than 2t plus 4, we made W tilde, which was W plus add some arbitrary vertices. Okay, this is what we did. And then we called a separator W tilde separator, then we called a W tilde separator, W tilde balanced separator S. So what is the property of this? S was here, and then I have connected components, and W was in each portion, right? In each portion, where what was the property? Wi intersection C was W by 2. And what did we do? We recursively on this, we recursively computed, okay, and then what we did? Recursively computed, we got returned Ti Fi for computing what? By giving graph induced on Ci union S, comma S union W intersection Ci. Okay, and what did we proved? We proved that this satisfies the invariant that size of W was size of this S plus W intersection Ci was less than equal to 2t plus 4, because we have to maintain. And secondly, we showed that any Gi, vertex set of Gi is strictly less than a vertex set of G, because W has, at least W has gone to one extra vertices. This is how we chose, and hence recursively we computed this Ti. And how did we got the tree decomposition for every? We added a root, Ti, T1, Tr, added all this and returned this. This is exactly what we did. Now I want to make precisely this algorithm constructive. Okay, so here is a trivial way of making. So which is the only step which is making this algorithm non-constructive? I don't know how to find S. If I knew how to find S, then I could have made this algorithm constructive. Okay, so one obvious way of getting this S is to apply try all possible S, right? I could just try all possible set S. Okay, so one trivial algorithm, or say XP algorithm. So what is our XP algorithm? Okay, so our XP algorithm will be, okay, replace find S by trying all possible subsets of size t plus 1, right? I have W, I just try all t plus 1 subsets. If it is, because if a graph has tree with T, then I know such a set S exists, right? So if I am not able to find S, what will I say? Is tree width is more than T, I have got a witness to the fact. Otherwise I will find this and I will progress, right? What will the running time of this algorithm? If you notice, T of n is going to be what? First of all, I could have, as I told you, right, I could, the way we did it, what is this? You have to be, let's do something funky, okay. It's actually summation. I don't know how many components are there, first of all. I don't know how many components are there, right? I don't know how many, okay. So I should write max over M, N1, N2, Nm, T of what? Ni, like Ni plus what? What was the size of S? T plus 1, right? So this is what? Max over these things, like number of components, I don't know how many, and N1, N2, Nm, such that summation of Ni is equal to N minus T plus 1. This is true, and plus N to the power T plus 1, because that is the time to find the separator. This is my recurrence. Okay, work hard. Okay, you can show this is N to the power big O T. Okay. Okay. Okay, Loki, let me repeat this for you, because if you miss here, it's all gone. So this is the problem we are trying to solve. We are given a input graph G and a number T. Either you say that tree width is strictly more than T, or return a tree decomposition of width order T. Okay. So what algorithm did we learn yesterday? It took a parameter graph G, a W, where W had size equal to 2t plus 4. So we said if what is this? If vertex set is less than equal to 2t plus 4, then you return a single node tree Tr, where f of r is the whole of vertex set. And what is the invariant we want to maintain? It returns a tree decomposition of width 3t plus 4 such that root contains W. And what did we do then? If w was less than 2t plus 4, then we made w tilde w plus some arbitrary sum vertices. Then we called w tilde balance separator S, which gave us some components, and then we recursively for each of them computed ti fi, where ti fi was a returning from when you called your algorithm on graph ci intersection S and S intersection w union ci. Okay, and what did we prove? We showed that the size of S plus w intersection ci is invariant correct 2t plus 4, and at least one vertex of gi is less than this, so inductively I can get an algorithm for this, and it returns me t1 to tl. I add r, make him adjacent to the roots, and this is my tree decomposition of width 3t plus 4. And now the only reason why this was not algorithmic, because S, we do not know how to find this S, and but what is the size of S? T plus 1. So one thing I could do, find S by trying all possible subsets of size t plus 1. Okay, I could do this. So but then the running time of this algorithm will be n to the power t plus 1 to check S. If no such S exists, then I have found a witness that tree width of this graph is strictly greater than t, and I can return that and I am done with it. Or I have found this S and I will progress further. So what is the running time of this algorithm? The running time of this algorithm is t of n, and look, I don't know after I delete this set how many connected components I am going to get. So doing max over n, and after I delete, first of all m denotes number of connected components. I also don't know what is the size of this connected component. So I am going to maximize over m comma n1 to nm, these numbers is the number of components, n1 to nm is the size of each connected component, and summation of ni I know is n minus k plus 1, t plus 1, because ni's are the size of this and S has size at most t plus 1 or t plus 1 exactly, because we are doing t plus 1 here. So the running time is t times ni, but look, in each gi you also add S, so you get ni plus t plus 1 plus n to the power t plus 1, and this you can solve to n to the power big of t. Okay, but let's solve something else for now, because so that we can keep this in head. Suppose this recurrence is some f of t times n to the power alpha. Suppose, then what does it solve to? Okay, let's try to understand this. So what we will do some trick, because look, it's much easier if this t plus 1 would not have been there, then you can show this is just like some n to the power alpha plus 1. You can show this is upper bounded by f of t times n to the power alpha plus 1. But unfortunately, the sum is not equal to the n, like, because we are also adding this t plus 1 everywhere. So I define, I define what I call t prime of L is equal to t of L plus t plus 1. This is what I do, a trick. Okay, this is my notation. What is t prime of L? Is t of L plus this is just recurrence solving trick. This is nothing funky happening here. Okay. Now I want to write this recurrence in terms of this recurrence. What happens now? Let's write down this is t prime some n prime, which is upper bounded by summation. What is this? T of, now let's write it down, max again over m, n1 prime, n2 prime, nm prime, and summation of ni is equal to still, what is this now? What is summation of ni prime? Is still equal to n minus t plus 1. Okay, ni prime. And now what I am going to write? It is t prime of ni prime plus f of t n prime, but here n was there. So what should I write here? Here I should write whatever this n is, I have to write, so what should be here? What should be here? Ultimately what we are substituting, look, you want to say t of n is equal to t prime of n prime, right? So what are you going to substitute eventually? what is n? What will be t of n? You will what will the value of n prime will be n minus t plus 1. This is what it will be. What will be n prime value is this, because t prime of this, what is, see, what is t prime of n prime is t of this plus some number, right? So if I call t of t prime of n prime, where n prime is n minus t plus 1, then what will I get t prime of n prime? This is exactly equal to t of n. This is just a normal substitution trick, but here I have n. So what is n then? N prime plus t plus 1. So this is why. So where we have to write n plus t plus 1 to the power alpha. Do you get my point? Okay. So I just did a normal substitution. Look, this is not this is not like I am not doing any parameterization. This is just a normal recurrence solving. Okay. There are many ways to understand this, but I prefer this way. Okay. Now we can apply induction and show that this is less than equal to, by induction on n and n prime and t, we can show this is f of t n to the power alpha plus 1. Okay, why? So let's see why. I'll just give you some region of seeing why, and then I will leave it for you to compute. I mean, this is not something which but there is reason why am I doing this. Okay. So why this happens? This is important. Now look at t prime n prime. N1 prime is strictly a smaller because of our property, so I can apply induction. So by inductively, this is what the number is going to be. F of t to the power n to the power alpha plus 1. Here what will I get? Here what I am going to get? I am going to get summation, let's forget alpha, okay, I want to show it's 2, okay, you can do it for alpha, I don't care, right, anyway we will have to do it when we do recursive understanding, but okay. So now this is what I want to show. So what will be t prime of n prime? Look, it is going to be f of t, it has nothing to do with this, and ni prime whole square. Do you agree? This is what it is going to be. Now I can take out f of t common from everywhere. What is left here? Summation ni prime whole square plus n plus t plus 1. Right? I have to show this is less than or equal to n square. This is all that I have to show. But look at this ni prime whole square. What is this? If I have a plus b plus c whole square is a square plus b square plus c square plus 2ab plus 2bc this. So if I substitute this, what will I get? Then I will get f of t times roughly n square minus all this, like I not equal to j 2 times ni n j, right, and plus n plus t plus 1, okay. Look, this is roughly quadratic term, this is linear term, right. So they will cancel out each other, right, and what you will get is some f of t times n square, okay. So the reason I did it with n square because then I can show you a plus b whole square. If I did with alpha, it will become a bit messy, okay, 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 good. So if you would had n to the power t, that n to the power t would have come out and some n to the power t plus 2 or 3 something would have come out, and then you can, okay. Anyway, that was not what I wanted to, I mean this is the recurrence we will get, and if you get such a recurrence we can solve this. So if I can replace finding this s with some running time of this form, right, then I will be happy. If I can find this s in this kind of running time, then I will replace this in this recurrence and I will get an algorithm with running time f of t times n square, morally, right. So how do we go about proving it? So our next step is to come up with an algorithm to find appropriate S in time f of t times n. Okay, so that's our goal. So this is what we are going to achieve next, and if we are able to achieve this, we will be happy. But look, you could if I could solve this problem, then you can give me W equal to Vg and you have solved me balance separator problem, right? But it's a bit different here. W has bounded size. Okay, can I make use of that? Okay, let's see. So I'm going to rub this part. This is just a normal computation. So let's try to understand this. Here's my S, here's my components. Okay? Question. Listen, madam, you will. Okay? This is how WIs are. Okay. Now, do you think we can get this S? Imagine for now, W1 is single vertex, W2 is single vertex, WL is single. Now do you know how to do it? It's exactly multi-way cut, right? And it doesn't matter if I wanted each these WI's to go into singletons, then I would say, hey, look at my W and give me a set of vertices which separates each WI and doesn't contain WI. Happy, happy. But the problem is WI may not be equal to 1. Who cares, man? What is the size of WI? WI is not very big anyway. It's like 2t plus 4. I partition. I guess I partition WI into W1, W2, WL. How many partitions are there? Right? At most t power, there are L bags. Right? Every vertex could be assigned. So it is L to the power 2t plus 4. Right? Or maybe L plus 1 because maybe some component doesn't contain. So doesn't matter. All I am saying, this gives me a t to the power big O of t partition. Now for each partition, I find a separator. What is the meaning of this? By definition, every connected component which is left cannot contain two of these guys. So I have ensured that this is it. So, and multi-way cut algorithm we have seen in the class, right? So I could use my multi-way cut algorithm and I can get this. So, n to the power t plus 1 enumeration, okay, t power t multi-way cut and partition of W. Okay, partition of W. And notice in T power T, I can, so in T power T, what I can do? I can guarantee width of size 3T plus 4. I can guarantee width of size 3T plus 4. Excellent. Now the next question, is it possible to get C power T algorithm? Natural, right? Okay, and let's do that. Okay. Yes, Sanjukta. Okay, let's call this W1, W2, W3, WL. Okay, good. It's really very, I am only interested in doing one computation of max flow, ST max flow. But now the problem is, imagine what I would like to do is following. I make a bag A, I make a collection B. A, I will add some WIs, B also I add some WIs, and I am going to call separator. I said I am going to call this guy as big S, and I am going to call this as big, and I am going to find ST separator between them. Then clearly I will find set of vertices which will separate A from B, clearly. Right? So after I delete, in the connected components cannot contain A vertices from A, and like the vertices of A and B will not be together because they are separated. But all of the A could be together for all that I care. Okay. So if I can somehow bound that both side A and B has some magnitude, they might be making some progress. Okay. But we know all this trick, no? Okay. So W1, W2, WL, okay, order them based on sizes, okay. So W1 is greater than equal to W2, greater than equal to W3, dot dot dot. It means I can find a partition A and B such that, what is the property? One third of W, 2/3 of W. Here 1/3 of W, 2/3 of W. Agreed? And I can find this partition in polynomial time. Given this polynomial time, I have no clue. But I know that there exists a partition of W. Now let A be union of W in here. Take all the union. Take all the union. It's a partition of W into A and B, where size of A is between between 1/3 of W and 2/3 this, and this I can enumerate again, right? I can enumerate all possible partition of W into W1 and W2 that satisfy this constraint, and then I find my separator S. What is the property? Now if I delete S, look at a connector component. Any connector component can either contain vertices from A or B. Even if it contains all the vertices of W of A, it cannot be more than 2/3 of W, right? And how much time this will take? Now notice, how many partitions of W are there? 2 to the power? How much?
You just want to partition A and B, so you want two partitions.
2 power?
2 power the size of W. Because we just want 2 partitions, but we just want A and B.
Okay. It could also be that some vertex of W is part of S for all that I know. Could be, no? But not the way we have tried to construct, right? I have always told you that I find S which, but I never told you that S cannot contain a vertex of W, right? That S could also contain vertices of W. Look, what did I say? It is not a partition of W, right? Because when we were making an argument yesterday, what did we say? Oh, look at W. At most t plus 1 can go from here and something go from here, and that is why we were choosing 2t plus 4, right? Otherwise, what is the point of choosing a t plus 4? I could use some t plus something, right? So that is why it's not one way. You decide whether a vertex of W goes to S, goes to A, goes to B, okay? 2 to the 3 to the power W. So the branching is 3 to the power W, and then whatever vertex is in S, you just delete it, and for the remaining you compute a max flow min cut, which you can do in k times n. Now the problem is, up until now my all the computations were based on that each Wi in the connected component has size at most half, but now it has changed, it is 2/3. So I need to change things. What I mean by this, look, now I am not guaranteed that Wi intersection C is W by 2. I am guaranteed that this is 2 times W by 3. Now, what should be the size of W? What should be the size of W such that at least one guy will split here? Otherwise, we cannot do anything, right? So, let's look at what I am trying to say here. Look, let's draw this picture and then you will understand. Here is S, here is connected component, I don't know. Okay? Here is your S, right? And here is your W, right? And what is the guarantee? Like each of Wi is at most 2 times W by 3. This is what is guaranteed. Am I right? Now, I would like to say that, look, when I look at this, its vertex set is at least, what? Look at the vertex set of Gi is strictly less than vertex set of G. And what was our argument? I said W is so large that you cannot accommodate whole of W here and here. So one must go here, right? So what is the size of W which can go here is t plus 1, right? Because we are computing min flow. So whatever S you will get, it will not have size more than t plus 1. Plus, whatever may be the size of Wi is, 2/3 could go here. So 2/3 of W could go here. What I want this number to be strictly less than W, right? I said, okay, t plus 1 of you go here, 2/3 of W went here. I want you to be strictly less than W so that I can say one vertex of W has come here. So then what is this number? It's like, if you notice, this guy will go this side. So t plus 1 is less than equal to, that implies 3t plus 3. So W should be strictly more than 3t plus 3, right? But when we were doing here, W had size 2t plus 4. So now I will make it 3t plus 4. otherwise my proof will not go through. But if it is 3t plus 4, then what are you going to return? You are going to return this plus t plus 1 extra, right? Right, because you, okay, so the tree decomposition which you will return is how much? 4t plus 5. But this is your algorithm, right? So I can find a separator in time 3 to the power 3t plus 4 times n. This is the running time of this algorithm. So if I plug in this, what will the running time of my algorithm will be? 3 to the power 3t plus 4 times n square for the overall algorithm, which is like 2 to the power big O of t times n square. And there was a lots and lots and lots of effort to get a factor 5 approximation for tree width in linear time, but that's a paper of CComp of Daniel and co, which is beyond the scope of this class. I could make this algorithm n log n, but that also will require extremely lot of hard work, which I will not do. Okay. Okay, so what you have seen, I cannot give you an algorithm to compute tree width exactly, but for all practical purposes, this is a good enough algorithm. What does it tells you? You give me a graph G, give me a number T, and either I will tell you the tree width is large, then perfectly, or I give you some approximate tree decomposition, right? So, and this approximate tree decomposition should be usable, okay? So, I have taught you almost everything which I wanted to teach you on tree width except how to do dynamic programming algorithms over graphs of bounded tree width, and that is what I will teach you tomorrow, okay? Some 2-3 examples, and hopefully that will be all for the tree width for tomorrow. On Saturday, at least my plan is to do one lecture on algebraization, one lecture on cut and count, one lecture on Seth ETH, and maybe one lecture on something. I still will not teach you kernel lower bounds in this course. Please learn it yourself, unfortunately. I mean, I will do it, so wait for my lectures. Every week you will see one video appearing of 3 hours, one day, and the algorithm which I told you, for computing tree decomposition, approximate tree decomposition, the first one is by Seymour and Robertson and Seymour. This is also their algorithm, and you will see the same algorithm appearing when I will do bisection decomposition and when I will do graph isomorphism for parameterized tree width. You will see exactly the same thing coming and coming. So this is the way we know how to separate things, and this seems to work as good as anything else. Okay, so I think until you have any questions, I will at least I'm done with the computation of tree width, and that is where I wanted to end today.